In the previous sections, we've been using different ways to list the elements of a set. So our sets, we're using word description, roster method, or set builder notation. In 2.3 here, we're going to use Venn diagrams to represent sets, and we're going to show set operations using the Venn diagrams. So let's see if we can shine some light on the idea of a Venn diagram. So figure 2.4 is an image of a Venn diagram. We have a rectangle, the letter U, we have a circle labeled A with some shapes inside, and then still within the rectangle we have a $sign, capital M, and the number 5. Now example 1 is asking us to determine each of the following sets. So what they're asking us to do is to list the elements of the set. So for the first one, it's asking for U. U is meaning the universal set. So let me put this right here, universal set. All right, so for part A, what we want to do is say my set U is equivalent to, and we'll use the roster method, and we're going to list each one of the elements contained in the rectangle or the universal set. So I have a square, I have a triangle, I have a $sign, capital M, and the number 5. And these are the elements of the universal set. If I look at part B, they are asking me for the set A to determine set A. Now set A, we'll say A is equal to, we're just going to look at the circle and what is contained within that circle. So set A is the square and the triangle. Part C says the set of the elements in U, the set of elements in U that are not in A. So if we look at the universal set, and if we remove what is included in A, we're going to go, let me write this down. This is in U, not in A. That's the set I'm trying to define. So the ones that are in U but not in A would be the $sign, the M, and the number 5. And that would be in U, not in A. So this is just using a Venn diagram to define your sets. We have another Venn diagram given in figure 2.5. You can see the rectangle and the circle A has 1, 5, 6 outside of that circle, but on the rectangle is 7 and 9. Use the Venn diagram to determine each of the following sets. So looking at part A, the universal set is what we need to define first. Remember, the universal set contains all the elements. So I will list all of these elements, 1, 5, 6, 7, and 9. That is my universal set. Then I'm going to look at part B, and they want us to define set A. Remember, set A is everything contained inside the circle. All right, so that is going to give me 1, 5, 6. Part C, it says the set of elements in U that are not in A. Once again, in the universal set, not in set A. So again, we're going to look outside of the circle, and that is going to give us a 7 and 9. And this is how you use the Venn diagram to define your sets. There are 4 types of relationships that can be shown in using a Venn diagram. The first one is called disjoint sets. All right, disjoint sets look like figure 2.6, where you have 2 separate circles. They do not touch or overlap, but they are contained in the universal set. Disjoint sets. The second one is a proper subset, and we know what a proper subset is. A proper subset says the conditions for that would be that set A is a subset of B and set A is not equal to B. So if you take a look at figure 2.7, you can see that set A is contained inside of set B, and you can also see set A is not equal to B. We will continue on to the next slide to look over the remaining relationships. The third relationship is equal sets. So if you take a look at figure 2.8, you can see that in this Venn diagram, set A is equal to set B, so they share the same elements. And that is what that Venn diagram would look like. The fourth one and the last one is the sets with some common elements. Again, you can see that in figure 2.9, you have two circles, set A and set P, and they intersect. And this area where they are intersect means that they have some common elements. All right, so they share common elements. And those are the four relationships that we have for Venn diagrams. We have disjoint, proper subset, equal sets, common elements. This Venn diagram is written on the left-hand side with the explanations for each of the regions. So they're using Roman numerals 1, 2, 3, and Roman numeral 4 for each of the regions. So if you have two sets that are intersecting, you will have 4 total regions contained in the universal set. And you can read each one of these if you would like to. I'm going to just go ahead and say if I have my sets, I'll say region 1 is going to be in A. So elements that are contained in A, not in B. All right, set that's for this Roman numeral 1 right here. All right, for the region 2, the elements are in both A and B. All right, so that's right in the middle. That's that common element, the sharing common elements. Region 3 would be elements that are contained in set B and not in set A. So that is this region over here, contained in set B, but the elements are not in set A. And lastly, we'll do region 4. That contains elements that are in the universal set that are not in A or B. And that's probably the easier way to remember these regions. Again, this is region 4 outside of those two circles. So if you have two intersecting circles in a universal set, you will have 4 regions. We are now once again going to use the Venn diagram to determine the sets. So using figure 2.11, we're going to define our universal set. Our universal set contains all the elements on that rectangle. And if you look, so all the regions 1, 2, 3, and 4, we're going to write all the listing out, and it would be set U is equal to A, B, C, D, E, F, G. All right, looking at part B, it says determine the set B. So set B is just circle B on your Venn diagram. You're going to look at regions 2 and region 3 and list out the elements. So set B is the set that contains D and E. Next, we're going to look at the set of elements in A, but not B. In A, but not B. So that means we're just looking at region 1. And in region 1, in this case, is just going to be A, B, C. Right, so that's region 1 once again. In A, but not B. The next one, D, the set of elements in U that are not in B. In U, not in B. So if we want to exclude B, we're going to focus on regions 1 and region 4. And if we write the elements in those regions, we will get A, B, C, F, G. All right, and then I'll go back to E, the set of elements in both A and B. Now we're looking at the circles once again, and we want to grab all the regions, and it has to be both in A and B. So that's going to be region 2, which is just going to give us element D. Again, all we're doing is practicing on how to grab the roster method of our elements by using the Venn diagram. We're going to learn how to go back and forth on these, meaning that you'll get your roster method and you'll form your own universal set or Venn diagram. So we are going to use this Venn diagram in figure 211 to determine the following sets. So for set A, we're going to focus on the circle, and we'll say set A is equal to, and that's going to give you region 1 and region 2, which is A, B, C, and D. All right. Part B is the set of elements in B, but not A. So if we're doing for NB but not A, we are looking at region 3 only. So this set is going to be defined by just the letter E, or region 3. Part C is the set of elements in U that are not in A. In U, not in A. So that way we're looking at, it's all in the universe, but we're going to knock out everything that's in A. So we're looking at region 3 and region 4. So in this case here, we'll have E, F, and G in the universal set that's not in A. Next, we're going to go back to that last one. Part D, it says the set of elements in U, not in A or B. Not in A or B. So that's just going to give you region 4. And region 4 is F and G. So you want to take your time when you take a look at these. Make sure you have them listed out. Sometimes it helps to write down everything in the universal set if you'd like to do that also. But make sure that you're looking at the correct regions. Definition of the complement of a set. The complement. So the complement, what we use is, we call it A prime, or it has a little knot right there. So this is considered as not A, not in set A. Right, so the complement is the set of all elements in the universal set that are not in set A. Again, a way they could represent this in set builder notation is right here. We call that A prime, or you can call it A naught, or not A. So if we look at our Venn diagram, obviously the circle is representing set A. That's everything inside the circle. And everything outside of the circle, but still in the universal set, is considered not A, or the complement of A. So for this exercise, we're going to try to find the complement. They defined the universal set for us. They said let U equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. Let say A be 1, 3, 4, 7. Find the complement of A, or find not A. So one of the ways you can do that is to take your listing of the universal set and knock out all the items that are contained in A. So A has a 1, a 3, 4, 7. The remaining elements are the elements that are not A, or the complement of A. And once you have those items, you can actually create your Venn diagram. And you'll see that set A here, that they drew our circle, has the elements 1, 3, 4, 7. And the complement of A is outside of that circle, but still contained in the universal set. For this problem, they're letting U, the universal set, be all the natural numbers through 1 to 20, it looks like. So they have listed 1, 2, 3, and ... to 20. That's my universal set. Then they're letting us know that set C is 1, 3, 5, ... 19. So notice the pattern on set C. 1, 3, and 5, they're odd numbers. So it will continue using that same pattern of 7, 9, and it'll go forward towards the 19. So those are odd numbers. Set C is the set of odd numbers. They want you to find the complement of C, or items that are not C. So if set C are the odd numbers, less than 20, then not C would be the even numbers. Write that down, even numbers again, and they'll be less than 20. So the complement of C should contain 2, 4, 6, and you can list them all out. To make it a little bit quicker, we can just say up to 20. 20 is an even number, I will include it in my set. So this problem is saying use the Venn diagram to represent the set not B in roster form. So if we take a look at our Venn diagram and we want the items that are not B, so I would actually just go in and mark through all the items that are contained in set B, and that would make my listing for not B all the other remaining elements. So 2, 6, 23, and 25 would be included in the complement of B. Make sure you read the instructions carefully when it says use a comma to separate answers as needed. Okay. So new definition, it says we are going to determine the intersection of two sets. So the intersection is defined by using A with an upside down U, B. A intersect B. And the definition for an intersection is the set of elements common in both A and set B. So we're looking for that area where they overlap. In that case, if you remember the Venn diagrams where they had the regions listed, it was region 2 where set A and set B were overlapping. So the formal definition here says A intersect B is equivalent to all values for X such that X is an element of set A, and, real important, look at that word and here, and X is an element of B. And means you have to satisfy both conditions. All right, so take a look at example 4. It says find each of the following intersections. So they listed the first set as 7, 8, 9, 10, 11, intersecting with the second set of 6, 8, 10, 12. If you take a look here, they both have the number 8 and they both have the number 10. So that is where they would intersect at 8 and 10. So that would be contained in that region 2. All right, let's look at part B. We have the first set of 1, 3, 5, 7, 9 intersect with the set 2, 4, 6, 8. So you can see the first set contains odd numbers, the second set contains even numbers. When you do the intersection, there are no elements in common. So if you think about that, that's that disjoint relationship where you have two separate circles. They do not overlap or touch at all. All right. And then we have the last one here. If you have the first set 1, 3, 5, 7, 9 intersecting with the empty set. All right, so the empty set does not have any elements, but we do have set 1, 3, 5, 7, 9. The answer, since they have no elements in common, is still going to give you the empty set. A further definition is the union of sets. We talked about intersection. Now we're looking at the union of sets. So the union of set A and B will look like this. A with a U for union, B. A union B is the set of elements that are members of set A or of set B or of both. All right, there's a lot of ors in here. So notice when we're looking at the formal definition, A union B is equal to all values for x such that x is an element of A or x is an element of B. So I think what you should have realized at this point is if we have A intersect B, we're using the word and if we have A union B, we're using the word or. Let's look at our next definition. It says the empty set in an intersection and a union. And we just experienced that one on the last slide when we did the intersection with an empty set. So it says for any set A intersect the null set will give you the result of the null set. If you're doing A union with the null set, the answer is going to be set A. All right, think of union as uniting them. So if I take all the elements in set A plus all the elements in the empty set, I'm still going to end up with set A. Let's take a look at some examples for union. So for A, we have the first set is 7, 8, 9, 10, 11, union with the second set, 6, 8, 10, 12. So think of union as uniting. The U as uniting. You want to unite all the elements in the first set with all the elements in the second set. So when we do the union, we will end up listing all the elements in both sets. Part B has the first set as 1, 3, 5, 7, 9, union 2, 4, 6, 8. So once again, we are going to unite all the elements from the first set with all the elements in the second set. And most of the time, if you can place these in ascending order, that would be great. Sometimes the numbers are not numbers, they're symbols, so you can just list them. All right, lastly, here we have the part C, the set 1, 3, 5, 7, 9, union with the null set, or considered the empty set. When we're doing the union, we're going to end up with the exact same elements on here. So this is going to give you 1, 3, 5, 7, and 9. And that would be your final answer for part C. You have a set uniting with the empty set, your answer is going to be the original set. Performing set operations. So let's see if we can take these one at a time. We have our universal set, which has the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And that is my universal set. Set A is 1, 3, 7, 9. And set B is 3, 7, 8, and 10. All right, so now that we know where our sets are and they just have them listed in roster notation, we're going to look at part A, which wants us to find the complement. That's what this means out here, that little tick mark is the complement of A union B. So we would do this just like we're working order of operations. We would find A union B first, which is what they did here, A union B, and they came out with 1, 3, 7, 8, 9, 10 when they did A union B. Now what you want to do is you want to compare A union B with the universal set. So take this item right here, compare it with the universal set. And on the universal set, what you want to do is remove A union B because we want the complement. So you can see they took out the 1, the 3, the 7, 8, 9, 10. And that left us with 2, 4, 5, 6. And the complement of A union B, the final answer, would be 2, 4, 5, and 6. Again, this is your final answer right here. Let me put it in a different color. Okay, let's take a look at that next problem, part B. It says the complement of A intersect with the complement of B. So what you want to do first is find the complement of A. So complement of A. We know what A looks like. So we're taking set A, comparing it with the universal set. We're going to knock out all those numbers that are in set A. So I'm going to knock out 1, 3, 7, and 9. And I'm going to write my complement, the remaining numbers. 2, 4, 5, 6, 8, and 10. All right, so that's my complement. And let me go in and clean this up just a tad bit. And we'll go find the complement of B next. We need the complement of B. So we're comparing set B with the universal set. Once again, we're going to take out all the elements in set B, 3, 7, 8, 10. The remaining elements are the complement. So that leaves us 1, 2, 4, 5, 6, and 9. All right, so once again, what we found was the complement of A, and then we found the complement of B. Let me see if I can get that cleaned up a little bit. So again, we want the complement of A intersecting with the complement of B. So basically, that is this first set, 2, 4, 5, 6, 8, 10. Sometimes we have to slow down to make sure we get the right elements. We want to know where they intersect at with the second set. So we're not doing the union, we're doing the intersection. Intersection is we want to identify what is in common. So if we take a look at what's in common, they both have a 2, a 4, 5, and a 6. So the intersection, or the final answer, would be 2, 4, 5, and 6. And that is the complement of A intersecting with the complement of B. This slide here is just a continuation from the previous slide, and we finished doing part B, and we came out with the complement of A intersect complement of B with the 2, 4, 5, 6. So this is just for you to review if you would like to do so. Example 7 is a great example for students to understand when you receive a Venn diagram. Do not get too distracted about what the elements are. Sometimes they have some crazy elements or some different unique looking symbols that are considered elements. And what you want to do is when you're focusing on union, intersection, complement, doing set functions, you want to go in and focus on the regions that you'll be using to determine your sets. So for instance, on this first one here, they have A union B, and A union B, without thinking, you just have two sets that intersect. Union means to unite. You're going to list all the elements. So the elements that you're going to list will be all the elements in regions 1, 2, and 3. So let me make these regions pop out just a little bit more for you. This is region 1, region 2, region 3. These are not elements. These are the list of regions, and region 4 out here. All right, so you can see for part A, we're going to focus on all the elements in regions 1, 2, 3. The complement of A union B the complement of A union B. So again, you're going to look at A union B first, which is everything inside the blue circles. And then you want the complement, so that's going to leave you with region 4. All right, and you can go through each one of these and verify each of the regions and the elements that are listed. And so remember, try not to get distracted by the elements, but focus on those regions that you need to add the elements together to create your set. So they give us our universal set, set A and set B. They want us to find the complement of A intersect complement of B. So the first thing I want to do is find my complement of A. Once again, I'll focus on set A and my universal set, and I will remove all the elements from set A in that universal set, which leaves me with the remaining elements 5, 6, 7, which create the complement of A. All right, next we will find the complement of B. So we're focusing on set B with the universal set. We will take out the elements of set B, 3, 4, 5, and the remaining elements will create our complement of B. 1, 2, 6, and 7. Again, that leaves us 1, 2, 6, and 7, the complement of B. So once again, we're looking for the complement of A intersect with the complement of B. So that would look like the set 5, 7 intersect with that second set 1, 2, 6, 7. Remember, the intersection is in common. That's the intersection. And we're looking for common elements. All right, so if you take a look, it looks like we have the number 6 and the number 7 would be the common elements. So our final answer here would be the set that contains 6 and 7. This would be our final answer that you would insert into the answer box as we select option A. Find the set, the complement of A intersects C. So what we should do first is find A intersects C, the items that are contained inside the parentheses. So I will go grab A intersect C. So set A is 2, 4, 6, 8. And we want to know where this intersects with set C, which contains 2, 3, 4, 6, 8. We already spoke about intersection. Intersection means in common. So they both have a 2, 4, 6, and 8. So the intersection result will give us 2, 4, 6, 8. But we don't want to stop there. What we actually want is A complement, A intersect C, right? We just found that, but we want the complement of that. So what we need to do is we need to compare our last answer, the 2, 4, 6, 8, with the universal set. So we want to compare these two items right here. Again, we're going to take the universal set and we will knock out the A intersect C items, which was 2, 4, 6, and 8. And that will leave us with the complement of A intersect C, 1, 3, 5, 7, 9. And this would be our final answer. So let's look at that one more time. We needed the complement of A intersect C to start with. So we focused on inside the parentheses. We found A intersect C. That was our first step. Once we found A intersect C, we compared the answer for A intersect C with the universal set to determine our final answer. So in this case, we will choose option A and insert our answer into the answer box. For this problem, they identified the universal set, set A, and set B. So that has all been given to us. What they're wanting us to find is A intersect B union complement of B. That may seem kind of ominous when you first look at it, but you want to do it in parts. Just like order of operations, we're going to go grab what's inside parentheses first. So we're going to grab the A intersect B. So for A intersect B, I'm looking at set A and set B and finding out what is in common. They both have a W and they both have an X. So A intersect B is WX. Now that wasn't too bad. The next thing we want to take a look at is to find the complement of B. The complement of B, or B complement. In order to do that, you want to focus on set B in comparison with the universal set. So once again, we're going to remove the elements of B, which is F, W, and X, and the remaining elements will create your complement. So I have A, H, M, P, and S, and that is my B complement. Go ahead and erase these items. Now that we have our two items, the last thing we want to take a look on here is to find the union of our two results. All right, so I'll write everything out here on the bottom. We have A intersect B, which we found to be W and X. We're going to take the union of that with the complement of B. And we found the complement of B to be A, H, M, P, S. Now, if you recall, when we're looking for the union of two items, we're just uniting all of them together. So I will place all the elements grouped together. So I'm taking the second set elements and I'm adding in the first set elements. And this would be your final answer that you would insert into choice A. For your final answer. Use the Venn diagram to represent the complement of A union B in roster forms. They want you to list the elements when you are done. So you can look at your Venn diagram and actually answer this question, and I'll show you how to do that. Let me first go ahead and write out what it would look like in roster form. Universal set would be all the elements from regions 1, 2, 3, and 4. So I will just list all these out. 2 and 27. Let me make sure that I have all of those. 3, 6, 7, 11, 14, 16, 21. It looks like we have them listed out. The next I would say set A. Just listing in each individual set. Set A is 3, 6, 7, 11. And set B. All right, so now that I have those safely placed on there, I'm going to just look at the Venn diagram. It says use the Venn diagram. So A union B is what I'm going to identify first. And I will draw a line encompassing A union B, means we're uniting them. So all the elements contained inside both circles would be A union B. The next thing that we want to do is we want to do the complement of that union. So that means we're going to exclude the elements that are in the union. And what that leaves you is 22 and 27 for the final answer. So you can actually just look at the Venn diagram and come up with your final answer. Or if you'd like to, you can always list everything in roster notation, such as what we did, listing each set and working from there. So just to make sure, I'm going to do it another way by looking at our listings of each set. So first thing I will do is I will grab A union B, focusing on set A and focusing on set B. Remember, union means to unite, so I would list everything. I have 3, 6, 7, 11, 14, 16, 21. That is a union B. And then when I want to do the complement of this item for the final answer, I want to refocus in on A union B compared to the universal set. All right, so this would give me the complement here. So what I will do now is take all the elements in A union B and exclude them from the universal set. So I will take out the 3, the 6, the 7, 11, 14, 16, and 21. And you can see that will leave me with the 22 and 27. So you can do this problem two ways, depending on how handy you are with reading your Venn diagrams. You can actually look at the Venn diagram and come up with the answer as we did up in the upper right hand corner, or you can do your listings. You can do your listings and come out with the same answer, 22 and 27. And again, you'll place this answer in that solution box on the software. Now this is an interesting problem. It states set A contains 18 elements, set B 13 elements. 6 elements are common to both A and B. And so we are looking for the number of elements in A union B. So we want to know the number of elements. All right, so since we're working with the number of elements, we're not working with elements, but the number of. One of the best ways to do this one is to realize that you have two sets and maybe do a Venn diagram. So since we have elements that are in common, I'm assuming that we have two circles that intersect. And I will place that in my universal set. And I'll call this first one set A, and the second circle is set B. All right, so when you're looking at a Venn diagram or creating one, the first place you want to start is where they have both sets intersecting. So that is going to be your region 2. So if you remember our region setup, this is region 1, region 2, region 3, and outside here is region 4. All right, so let's take a look at what has been given. We do know that they have 6 elements in common. So that means region 2 will have the number 6. There's 6 elements that they have in common. What we want to do is to fill out the region 1 and region 3. We know that set A contains a total of 18 elements. So since circle A has a total of 18 elements. And again, we're focusing on circle A here. Let me make that a little more bold. We'll do 18 minus the 6 in common will give you a total of 12 elements. So we have 12 elements. So region 1 plus region 2 is set A. So 12 plus 6 gives us 18 elements. Now focusing on B, and let me make that a different color here. So we're going to take a look at set B. Set B has 13 elements in total. So I will take the number 13, subtract the 6 that is in common, and that leaves me 7 elements in region 3. And if we want to check on that, we can say set B is created by region 2 plus region 3. So 6 plus 7 will give me a total of 13 elements. And now that you have regions 1, 2, and 3 completed, you should be able to go in and find A union B. A union B, uniting them, is telling you to take region 1 plus region 2 plus region 3. So that will give you 12 plus 6 plus 7, or a total of 25 elements. So this would be your final answer, 25. So once again, we used a Venn diagram to create the regions so that we can complete each region and add it together. For this problem, they gave us the identification in set builder notation for the universal set and sets A, B, and C. The question asks us to find the set A intersect the universal set. And that doesn't mean union, that is the universal set. So what we should do first is to redefine the universal set and set A in roster notation. So here's my universal set. The universal set is all x's such that x is a natural number and x is less than 6. So natural numbers start with 1 and increase from there. And we want to stop at the numbers that are less than 6. So 1, 2, 3, 4, 5. We'll redefine set A in roster notation. And it says all values for x such that x is an odd natural number and x is less than 6. So odd natural numbers would be 1, 3, 5. And we stop there because those are less than 6. Now we can focus on the question we need to answer. We want A intersect the universal set. So we're focusing on set A and universal set, and we want to find the intersection or items that are in common. So notice they both have a 1, a 3, and 5. So the intersection result would be 1, 3, and 5 items that they have in common. And this would be your final answer. So you want to carefully look over to the side to make sure you select the right answer. And we are matching answer number A as an apple. A palindromic number is a natural number whose value does not change if the digits are reversed. So if you rewrite the numbers in different order, the first number becomes the last number, and the second number becomes the second to the last number, and so forth, the result would give you the same identical original number. And examples of palindromic numbers are the number 11. So if I reverse those number ones, I'll get the same answer. 454, let me just give you an example. So this is 454. So if I take this last 4 and I make it the first 4, first digit, And if I take the 5 and make it the second digit, and I take the first 4 and make it the last number, you will see that I have identical numbers. I started out with 454 and I ended up with 454. So that's what they mean by reversing the numbers. So reversing the numbers and getting the same result gives you a palindromic number. It says, use this definition to place the number 33 in the correct region of the Venn diagram. So we have the universal set is the set of natural numbers. Set A is the set of palindromic numbers. Set B is the set of even numbers. All right, so from what I'm understanding then, A is palindromic, B is even. So for B, even numbers are all going to fall between region 2 and region 3. So I'm going to take each one of these regions and just give you kind of the definition for that. So region 1 would be that it's falling in set A, so it's palindromic. And since region 2 and 3 are the even numbers, then this must be the odd number, palindromic and odd number. Region 2 is that holds palindromic numbers that are even, palindromic and even. And since region 3 is not included in set A, this is going to be an even number that is not palindromic. All right, and then we have region 4. So region 4, remember set B is even, so that means anything outside of B or the complement of B would be odd. So region 4 would be odd, and again, it's out of set A, so it is not palindromic. All right, so when we want to place the number 33, you identify that the number 33 happens to be an odd number. So that's going to be in region 1 or region 4, but 33, if you take these numbers and replace them in reverse order, it is palindromic. So 33 is odd and it is palindromic. And therefore, that is going to go into region 1. This last slide is introducing you to the formula for the cardinal number of the union of two finite sets. That sounds kind of wordy, but you actually do know what this means. The cardinal number is the number of elements contained in a set. We talked about union is to unite two sets, all the elements. Finite means that it's countable. We can count how many elements are in the set. So the formal definition for this is the cardinality of A union B. The cardinality, the number of elements in A united with B, is equal to the cardinality of A plus the cardinality of B minus the cardinality of A intersect B, or the region where they overlap, the intersection. All right, so we have a Venn diagram here. Set A contains 1, 3, 4, 7. Set B is 3, 7, 2, 5, 6, and region 4 has 8, 9. Again, if you want to, you can rewrite each of these into roster method if you'd like, but you really don't need to. We're looking at the cardinality of A union B. So we want to look at A union B, and I'm going to highlight A union B means to consider everything that is contained inside the two circles together. Cardinality means the number of elements. So if I want to count the number of elements, I would count 1, 2, 3, 4, 5, 6, 7. It did not ask me to list the elements. It wants to know the number of elements. So the cardinality for A union B is just 7. We're focusing in on A union B first, and then we count the number of elements contained. All right, so let's go in and get this cleaned up, and we'll grab that second problem there that is asking for the cardinality of the intersection of A intersect B. All right, so cardinality of A intersect B. So A intersect B, the part that they have in common, I will highlight this is going to be the region where they overlap at. All right, and it wants to know how many elements do we have here. And we have the number 3 and we have the number 7. So we have 2. And we have 2 elements. All right, so that is the easiest way to do those 2 problems. When we're looking at that formal definition of the the cardinality of A union B, we can actually work that out differently if you want. I'm going to take this one and rework it differently. So we know the formal definition says the cardinality of A union B is equal to the cardinality of A plus the cardinality of B minus cardinality of A intersect B. All right, so if we look at the cardinality of A and we were to count how many elements are contained in set A, we would see that there are 4 elements. All right, so that's going to give me 4. If we count the number of elements in set B, that's 2, 3, 5, 6, 7, that is 5 elements. And then we subtract, that's supposed to be a subtraction sign. We're going to subtract the cardinality of A intersect B. Now the intersection contains exactly 2 elements. That's the number 3 and number 7, region 2. All right, so the intersection of A intersect B contains 2 elements. So if we were to take 4 plus 5 minus 2, you're going to get 9 minus 2, or 7 elements, and it matches. You have 2 ways to do this. You can look at just your Venn diagram to determine the number of elements by counting them, or you can use that formal definition, which always works.